So today I wanted to talk about this star that none of us can see. It's right now it's about a 10th magnitude star. So if you look at the stars in the sky, not tonight, but on a typical clear night in Jacksonville, you might see third, fourth magnitude stars. The brightness of stars historically was based on a ranking system. Magnitude one would be the brightest stars that we can easily see. Magnitude two would be kind of the second rank, three, and so on. And if you go to a really dark sky site, you might see all the way down to magnitude six or even seven. Certainly not in Florida, though, or in Jacksonville. But you might recognize some of these constellations. Hercules is a really great constellation to get to know. There's the nice Keystone sort of square that has Messier 13, which is a fantastic globular cluster. And you can see bright stars Vega and Antares. And so Corona Borealis is this tiny constellation nestled in between Hercules and Bootes. And it contains roughly seven brightest stars, makes a nice little crown. Here's T Corona Borealis. And it's a really interesting star, but you have to have a pretty nice telescope to be able to see it. At least there will be a change roughly sometime in the next, I don't know, day to 6 months. This star is going to become almost as bright as Polaris, the North Star. So here's just a spotter chart that I made using Stellarium. You could probably pick out Polaris if you've got a compass or if you can spot some northerly constellations like Cassiopeia and the Big Dipper or the Little Dipper. Well, you may have more trouble with T Corona Borealis, but for the next few weeks, right around sunset, if you look due west, actually for the next week or so, for the next night, this was tonight, you'd see the crescent moon and you should see the bright planet Venus setting in the west. And so if you go straight up, almost due west, you should be able to spot it. So when this star brightens, which should hopefully happen sometime soon, it'll actually be visible to the naked eye. And so this is kind of spectacular. This kind of thing almost never happens where you have a new star in the sky, one that you can't see, but then all of a sudden you can see. This idea of a nova, there's lots and lots of records dating back thousands of years. As long as people have been studying the sky, people have noticed new stars, but it was a pretty rare phenomena. And the term nova, which is of course Latin, comes from the great astronomer Tycho Brahe, who was a Dutch astronomer that made several discoveries, but he noticed that there was this new star visible during the day. It wasn't very hard for him to notice. It was visible during the day for 2 weeks. I'm sure he wasn't the only person that noticed this star. And it actually stayed in the sky visible to everyone for about 1.5 years. So this was a very confusing thing. What causes this new star? And it turns out today we know that it was an extremely energetic event. We don't call it a nova anymore. We call it a supernova. These are some of the most energetic explosions that happen anywhere in the universe, and we can see them all across the universe. And so they're wonderful tools for astronomy to study like how our universe is evolving and how we can understand that our universe had a beginning. However, this supernova was very, very far away, and there are much smaller explosions that actually do happen on stars that we still call novae. And there's about 10 of these that happen every year. So, okay, we have 10 of these a year, but we can't see almost any of them. It's very rare that you know of a nova that can be seen just with a naked eye. Most of them are just too far away. And also, it's extremely rare for us to know that it's going to happen. Usually, nova are surprises. And T Corona Borealis is going to be one of those rare, there's only about 11 of these known in our galaxy, things called a recurrent nova, a nova that happens again. And T Corona Borealis brightens about every 80 years. We can see this in the historical records. So I don't know why this is the case, but apparently comets are bad omens. The last comet I saw was in 2020 during COVID, but nova are good omens. So here's to looking forward to some good news coming soon. All right, so T Corona Borealis is often called the blaze star because, as you can see, it blazes pretty bright. This is what's called a light curve, and it's historical. This is the last time that this star went nova, had this amazing outburst and brightened to, you can see it's about third magnitude there, but they actually missed it at its brightest. So it may brighten to 2.5 or even 2 magnitudes. And what's really, there's a lot of really interesting things going on in this light curve. But what's really interesting to me and to people predicting novas is that there's this dip that happens um, almost a year, a little bit less than a year before the actual nova explosion outburst. And you can see there's also like a second hump. There's all kinds of interesting features in this light curve to try to understand that tell us about what's actually going on. But the prediction for this coming any day now is based off of this 1946 light curve that shows us the features that we expect this to happen more or less exactly like this again. And of course, that may be wrong, but it's a pretty, well, it's a pretty solid bet. We'll see if it pans out. What is a recurrent nova? So it's actually not a single star. What we're seeing is actually two stars in a really close binary. And one of those stars is really not a proper star. It's called a white dwarf. It's the core of a dead star that's not doing anything except sitting there in space and actually having mass. So it can actually have material fall onto it. And if it's close enough to a big companion star, that companion star can actually become big enough that it loses some of its outer atmosphere to the gravity of the white dwarf. And this white dwarf forms this accretion disk, almost like you would have when a star and planets were forming. And this accretion disk, builds up and becomes very hot because all this gas is crashing into itself, but eventually feeds the white dwarf. And as this white dwarf gets fed, it gets more mass and more mass and more mass. And all of a sudden, what was inert, just dense material suddenly has enough hydrogen to reignite and have a small explosion on the surface of the white dwarf. And when I say small explosion, I mean extremely energetic explosion, like millions well, many millions of TNT. The white dwarf just on its own is actually brighter than our sun. And that's because it's so hot. And as this material falls onto it, it heats up even more. And so eventually it obtains like the pressure and temperature that you can have fusion like you would have in the core of a star where you have temperatures of millions of degrees on its surface. And this explosion is still not energetic enough to break apart the white dwarf. And that explosion is what we see as a nova. So how do you get this incredibly big star? Well, actually take a look at our sun first. The sun is what we would call a typical low mass star. And we kind of measure all properties of stars in relation to the sun. So the life of a star is very different depending on what its mass is. A star like our sun, it might live for 10 billion years. And we're about halfway through the sun's life. But about 9.5 billion years into its life, it will actually run out of hydrogen in its core. And most stars, they work by fusing hydrogen into helium, hydrogen being the most abundant element in the universe. If you put it in high pressures and temperatures, you can cause it to fuse together and form helium, and that releases energy. And it doesn't release much energy, but there's so much hydrogen in a star that when you add it up, it releases an insane amount of energy. So our sun, in about 4.5, 5 billion years, it will no longer be fusing hydrogen in its core. So what's going to happen to it? Well, as it fuses hydrogen into helium, that helium doesn't fuse. It just kind of sits there. It's inert, and it stays in the core of the sun like a pollutant. But eventually it builds up to become most of the core of the sun. And so it starts to change the structure of the sun. And actually, very, very slowly over time, the sun is growing brighter. And so you'll actually see over billions of years, the sun getting slightly brighter. Because helium is very dense, this is actually, and it's serving as mass, it's causing the core to shrink. And eventually, the helium core will shrink to such high density and pressure and temperature that it itself can ignite. And this is called a helium flash. Essentially, the whole core ignites at once. And you might think, oh, there's going to be a giant explosion, but that explosion happens inside the sun. And so by the time that energy travels out to the outer edge, we never see a helium flash. It just adds energy to a star, which causes it to slowly brighten. But that will change the structure of the sun, and the sun will become much, much larger. It will become something called a red giant, which will probably engulf the orbit of the Earth. So here you can see the sun today is quite large. It's more than 100 times the size of the Earth. But if you look at the distance between the Earth and the sun is only about 1% the distance. And yet, when it becomes a red giant, it will be increasing in size by 100 to 200%. And it will engulf all those nice little planets, Mercury, Venus, and Earth, in the inner solar system. So these stars are incredibly huge. And because they're so big, you can have two stars actually, like the sun, two stars in a binary together that were orbiting each other and not really interacting with each other, just living out their lives. Suddenly, they've got this giant red giant star. One of them turns into a red giant, and now they're interacting. So that's what happens in nova. And actually, that's kind of the end for our star, the sun. It'll become, at some point, it won't be able to fuse helium into heavier elements anymore. It'll have a kind of inert carbon core, and that core will just stay there while the outer layers of the sun will kind of float away. They'll be blown away by the extreme temperature and pressure of the core. And you get this beautiful planetary nebula, like the Ring Nebula shown here. That tiny white dot in the center is a white dwarf that has about roughly the mass of the sun, or half the mass of the sun, somewhere in that range. It's about the size of the Earth, and its temperature is initially millions of degrees, whatever unit you want to use. So that central star is so hot that it actually irradiates the surrounding gas and dust and causes it to light up the way that we see it. Interestingly, if you look at white dwarfs, they're not really stars, although they're really bright, so they're still characterized as stars. They're composed of matter that is so dense that it's roughly the density of an atomic nucleus. So you can imagine just like carbon atoms almost touching each other in almost like a crystal structure. In some perverse way, it's kind of like a giant diamond, right? It's not the same crystal structure, but it's a crystal structure. And what happens when you get carbon atoms and actually the electrons in the carbon atom orbitals so close together is that there's actually a new physical force that comes into play called degeneracy pressure. And this is due to the rules of quantum mechanics. But an easy way to think about it is, imagine I'm sure there's lots of people sitting in the audience, and there's only a certain number of chairs. If there's lots of chairs, you're all going to spread out and you'll have plenty of space. But if there's a lot of people and not enough chairs, all of a sudden you've got some pushing of elbows, and it becomes difficult for everyone to find a spot. And so this will lead to some like pressure that actually causes the electrons in the atoms to move faster than they otherwise would. And that acts as a repulsive extra force. So when you start to confine these electrons through such high densities, so essentially having a sphere the size of the Earth with the mass of the sun, this is what keeps the star from actually collapsing further. But this pressure is constant. It's just a property of physics. And so even if you add more mass, the star actually doesn't feel any extra force. So you slowly collapse the white dwarf. You make it smaller and smaller and smaller, and it can actually heat up and enter higher pressures. So if you've got a big red giant companion nearby, it has a white dwarf that's close enough. It doesn't have to actually be, sometimes the white dwarf can be inside the red giant, or sometimes it could be touching the red giant. But as long as its gravity is close enough, red giants are actually kind of unstable, so they'll pulsate. Sometimes they'll get bigger and smaller. And they have really violent winds as material blows away. Because they're so big, the gravity at the surface of the star is very low, and so it's very easy for those outer layers to get thrown off into space. And a lot of that mass can transfer over to the white dwarf, which again doesn't have anything going on, except now it's accreting material from the red giant, mostly hydrogen, and eventually can build up an atmosphere that can undergo fusion again. And when that happens, we get a nova. So here's an animation made by some NASA animators about what a nova looks like. You can see the red giant star has its accretion disk, and the white dwarf is really small here, but you can see this other hot accretion disk, and there it went nova. So enough mass was added onto the white dwarf that it could ignite, and it causes an explosion out. And that explosion actually sweeps back into the surrounding material in the red giant and can cause shock waves that can accelerate particles and reach really fast speeds. So there's a lot that actually goes on with this nova. And so going back to the light curve, what we're seeing here is actually in 1945, there was a dip before this explosion. And that dip is still a big mystery. Something's happening to block some of the light from the companion star. And it's likely that dust is being created from high densities. Maybe a wind is starting to erupt. Something is going on there. And the accretion rate increases slowly. So more matter is falling onto the white dwarf. And eventually you trigger that threshold where the white dwarf has an explosion on its surface. You get the nova, which fades away in time. And then there's this mysterious second peak, which we think astronomers have explained in the last maybe 5-6 years. And so focusing on the light curve, you can see for T Corona Borealis, just in the real recent last few years, this is mostly data collected by amateur astronomers, the AAVSO, the American Amateur Variable Star Observers. They have been tracking T Corona Borealis and have seen this dip. And there's this sinusoidal modulation that actually corresponds to the period of the binary. So we're actually seeing mostly light from the red giant star, not so much from the white dwarf. Although there's flares from the accretion disk. The accretion disk is all this material that's really hot and material falls in and things. So that can actually brighten and fade. And so you see in the blue, there's sometimes these fluctuations from the accretion disk. But that sinusoidal period is just the red giant, which is elongated, right? Due to the gravity of the white dwarf. It's actually tilted with respect to us. And so sometimes we see a little bit more of its area and sometimes we see a little bit less. And that causes these modulations that fit the 228-day period of the orbital binary. And so when will it happen? This is what you're all here to hear, right? So if you fit the historical data and the more recent data, so you can see this is, again, all from AAVSO and historical data. What happened in 1936, 46, if it repeats again, we would expect that this would happen on September 29th, 2024. And this used to be a much wider, I didn't put the error bars here, probably plus or minus 3 months. And this is somewhat uncertain. But you can see here, because we've seen this dip, we should expect it very, very soon. And very likely by the end of the year. So all the astronomers now are really excited about this. It's one of the closest nova that we'll get to study. And so there's all these proposals in to point telescopes at it as soon as it happens. And it should be really interesting. Maybe we'll find out new things about nova from studying it. And hopefully you'll be able to see it as a bright star in the sky. I wanted to tell you a little bit more about what we're going to learn about nova from this. And a common misconception, even with Tycho Brahe, right, was that a nova and a supernova are not the same thing. So T Corona Borealis is not a supernova. This shows a different nova, T Pyxis, which was detected by the Hubble Space Telescope. And you can see these beautiful little knots of ejecta from very old nova eruptions that have been thrown out into space. And this is not to scale. If I had made this to scale, this would be roughly to scale. So you can see the supernova that happened in 1006 AD that was seen by Chinese astronomers, much, much larger today than even these tiny uh, nova shells. So the scale of the eruption is vastly different, but it's actually a mini particle accelerator. It works very much like a supernova remnant. And so here's a schematic on the left and an artist's rendition on the right, showing you've got a red giant with a red giant wind kind of flowing out. And then when the nova goes off on the white dwarf, it actually creates this explosion that gets driven vertically, so down and up, because there's all this mass in an accretion disk around it. And so that shock pushes out, like making two bubbles, and actually runs into a lot of material and works just like we have in supernova. We have shocks accelerating particles. And one of the things that I'm really interested in is trying to understand where all the cosmic rays come from, these very energetic particles that surround us and are always bombarding us from space. And it turns out nova explosions are a great way to justify our models for supernova remnants, just at much smaller energies. So you have a white dwarf, a thermonuclear explosion on a white dwarf, it runs out into material, and that shock wave can accelerate particles. And this all happens on astronomer timescales, human timescales. So astronomers can study it. We don't get a few year snapshot, right, of a supernova that may have happened 1,000 or 2,000 years ago. We actually get to see the particle acceleration and the explosion in the matter of days to weeks to months. And so these particles that are charged, electrons and protons, they actually hit into the shock, and magnetic fields, which are twisted by all the fluctuations in the shock, accelerate this. They allow some of the shock energy to go into the particle energy, increasing its momentum and kinetic energy, until eventually that particle can escape from the turbulent magnetic fields. Its gyro radius around the magnetic fields become larger than the scattering. And so we have actually seen this with gamma ray telescopes detecting nova. This only happened about 10 years ago, the first detection of a nova with gamma rays. And this is about 3 years old, where two different gamma ray telescopes at two different energies detected the same nova. And they actually saw the nova in the lower gamma ray energies peak, and then the higher gamma energies peak. And this corresponds to different energy particles being accelerated on different timescales, and is a really nice demonstration of the same kinds of particle acceleration that we see now in not just supernova remnants, but probably many other things. So these are wonderful demonstrations of the physics of particle acceleration. And it turns out they also make these really beautiful pictures. There is no nova that does not recur. What makes recurrent nova special is that they reoccur on timescales that are maybe 10 to 100 years. So human timescales where we can say, we'll see this again, or we have realized we'll see it again. Many, many other nova will happen in a similar way, but the accretion rates or parameters of the system are different, where it might happen every 100,000 years or maybe even longer. And so we haven't had enough human history to realize that these are also recurrent novas. But you can see many of these novas, when they're studied, show these shells around them that show evidence that there were actually these explosions many, many years ago, maybe 100,000 or even millions of years ago, that have just moved out into space and cooled down and clumped up to form these little ejecta pieces that can be then seen when there's a new nova, as the light actually hits these clumpy dust clouds and reflects back to us. So what you see there is called a light echo, where the really bright nova went off, and then that light actually traveled and bounced off of some dust. And so weeks or days later was seen with the Hubble Space Telescope. And that allows us to sort of see what the dust structure is around these stars. And it turns out, this was about 2 years ago, there's something now called a nova super remnant, which is totally confusing. It's not a supernova remnant. It's a nova super remnant. It's about the same size as a supernova remnant, but it is not around a stellar explosion or of a destroyed star. It's around a nova. This is actually first seen in the Andromeda galaxy. And this is about as big as a supernova remnant, but it's composed of millions of years of reoccurring nova. that have driven these shocks that collect and sculpt out this big bubble in space. And this was not expected at all. And in fact, was only discovered in a different galaxy because they had very, very sensitive Hubble images of the Andromeda galaxy. In our galaxy, it was just too close to see. It would be too faint against all the background stars. And so once this was realized, people have now gone and searched for these in our own galaxy and are starting to find them. And there's one nova super remnant that's been found around a nova that was not known to reoccur. It just went off once that we've seen, but it has this giant remnant around it, which means that it's a recurrent nova that we'll see happen sometime again. So there's all kinds of interesting things that nova can tell us about the environments around them and how they happen. And actually, a good question though is, can you ever have a nova go supernova, right? Nova are small enough explosions that they don't break apart a white dwarf, but if you get a big enough explosion, that should break apart the white dwarf. And it turns out it's possible. We've never seen it happen, but it's possible that recurrent nova stars could go supernova. The idea about white dwarfs was really put on good theoretical basis by Subramanian Chandrasekhar, who was an Indian astronomer who came up with some equations of stellar structure on a very long boat ride from India to Cambridge, where he was going to start his first postdoctoral fellowship. And he combined the laws of stellar structure, which he knew well, and quantum mechanics, which were just developing, and realized that as these gases, we call it a gas, but as the material in a white dwarf gets under extreme pressures, right, where you have that degeneracy pressure, it becomes relativistic. And so it follows slightly different laws of physics than classical physics. And so because it's relativistic, there's actually a limit at which you can have a white dwarf. If it's more massive than this limit, it can no longer maintain its structure. That degeneracy pressure is overcome by gravity. And so Chandrasekhar predicted that there should be no white dwarfs more massive than about 1.4 times the mass of the sun. And this was very controversial at the time, but is now widely accepted as true. And so what happens when a white dwarf exceeds the Chandrasekhar limit? Well, at that point, the entire core of the white dwarf becomes unstable and can participate in fusion. And so you would have the entire star become destabilized and release all of its energy, and you would get a supernova. And these are called type 1a supernova for historical reasons. But there is about 10 to the 51 ergs of energy released. And for a long time, it's been predicted that type 1a supernova are caused by white dwarfs. But there's actually two scenarios. So one is that you have one white dwarf that's in a nova system that eventually exceeds the Chandrasekhar limit because it's stolen enough mass from its companion giant star. But we now know that there are gravitational waves that come from really massive objects in tight binaries. We've seen black holes merge with LIGO, the Gravitational Wave Observatory. We've actually seen neutron stars merge, but we have not yet seen white dwarfs merge. And so if you had two white dwarfs, let's say that T Corona Borealis, the red giant, doesn't give enough mass to the white dwarf for it to explode, the red giant will eventually become a white dwarf, and there'll be two white dwarfs in a close binary sitting with each other. Over time, that binary will decay as its gravitational waves move away, and they get closer and closer until they crash into each other, causing what's called a double degenerate explosion. And I think we're very close to understanding maybe both of these are viable mechanisms, maybe one is preferred in nature over the other. And understanding which one is correct or dominant will really help us understand type 1a supernova and how we use them for cosmology. And we come up with all these great ideas about dark energy, causing the universe to accelerate in its expansion. That's all based on our understanding of type 1a supernova. So I hope that sometime, hopefully very soon, you'll get a chance to look up in the sky, and for a few days, maybe only one night, you'll get to see this new star, T Corona Borealis. And when you see it, it'll be a cute little star. Think about all the really insane things that are happening to make that star visible and all the really cool science that we're going to learn from it. So thank you very much. And I'll just put up a plug for our future astronomy nights. We've got a great lineup for the rest of this fall semester, and it'll be the first Friday of every month. So I hope you can make it, and I hope we have clearer skies.